next video, I will show you the first method of finite element formulation. It is called the direct stiffness method. Actually, for this one, I think you have learned it somehow before when you study, I think, in the course of structural analysis, specifically the matrix structural analysis. I believe you would learn something about this before. Okay, so I think for this course, it would be a good start for us to learn this first because the element equations derived from this one is, I think, it's easy to understand. Then for structural problems, in particular one-dimensional problems like beams, trusses, and frames, it's very suitable to adopt this one because, as I told you, element equations are easy to derive. It's also can applicable for other 1D problems in other fields, like in mechanical engineering. You study heat transfer or fluid flow. Okay, you can apply this one as long as you can derive the stiffness equation. For 2D, 3D problems, of course, you can apply this one, but to derive the stiffness equations or element stiffness matrix, maybe there are other methods that we will show you later. It may be more appropriate. So in this case, we focus on 1D structural problems. Okay, that is truss element and beam element. Okay, we start with truss element. Okay, suppose you have a truss element like this. It's length L. Okay, length L. Yeah. Okay, E and A for this element is assumed to be constant. So it's constant element E and A. Okay, and this element consists of two nodes. Okay, this node and this node. The first node is located at x equal to 0, and the other one is x equal to L. And at both nodes, you have you will see this. You have F and U at both nodes. Okay, F represent nodal force vector, and U, of course, represent nodal displacement or nodal degree of freedom. What you need to do is try to relate nodal force vector and nodal degree of freedom here, okay, for this element. Okay, and the one thing I like you to see is that this element, there is no load apply over this element. Okay, now to derive the equation that relate F and U, we use the basic mechanics. Okay, that you learned before, or most of you learned in the class in previous course, advanced measurement. Okay, we have equilibrium equations, constitutive equations of Hooke's law, and strain displacement relationship. For equilibrium equations, of course, since it's truss element and it's 1D problem, so you have one equation here. Okay, you have summation F equal to 0. So what you have is F1 plus F2 equal to 0. And also we have we define stress also equal to F over A. Okay, in this case we define as F2 over A. And then for Hooke's law we have stress and strain relationship. Okay, this is like a really equation that should be really familiar to you. For axially loaded member, we have axial stress related to axial strain via Young modulus. And we also have a relationship between strain and displacement here. Okay, strain would be equal to, okay, if you learned advanced measurement and you remember, okay, axial strain would be change in length per unit original length, right? So change in length here would be U2 minus U1, okay, of this element divided by original length L. So this is strain. And from these three equations, okay, you can derive relationship between F and U. Okay, you can start with from stress here, okay, equal to epsilon times strain, and you put strain equation in here, okay, and you put here in here, you can have this equation. then since F2 equal to minus F1, you can also have equation here. So if you look at this two equation, F2 here and F1 here, now you have relationship between F and U, and you can write those down in the metric form here. Okay, so this is basically the element stiffness matrix for a task element that we have. Okay, and we can define the whole thing here as K, which is element stiffness matrix, and here U would be nodal displacement vector, and this is of course nodal force vector here. Okay, so this is what we have. So basically, this is element equation for a task element. Okay, and you can apply this one to solve the problem for 1D problems that involve a task element. Okay, and for this element, okay, if you have the element like this that represent the task element like this, it means that displacement within this element is actually given by linear approximation here. Okay, so Ux is the axial displacement at any point within the element, and it can represent by linear function like this. A1, A2 of course are constant. Okay, and you can represent this Ux in terms of nodal displacement U. Okay, like this. And this equation, the metric n that relate the displacement approximation here and nodal displacement here, we call shear function. Okay, so this is basically a shear function for this element, and this shear function is given by this equation. Okay, and n1 is look like this, and if you plot n1 along the element length, you will see the graph like this, and n2 here is given by x over L, and if you draw the graph, it looks like this. Okay, and you will see that both shear functions are linear functions. Okay, so it means that if you represent your task element by this equation, you assume linear approximation within your element in terms of displacement. Okay, because you will see that both shear functions are linear. Okay, linear. Okay, you will see a lot of this shear function later. Okay, especially in my part. Okay, so you will know that if you use this element approximation, you assume linear. Okay, and I can show you this. Okay, look like this. So this is like a task element. You have node 1 and node 2, right? So the nodal displacement vector for node 1 is U1, and nodal displacement vector for node 2 is U2. Okay, and to derive shear function, okay, we start with the linear approximation for this element U equal to A1 plus A2x. Okay, we don't want A, so we solve for A. So basically we eliminate A because we try to relate this Ux and U1 and U2 here. So at this node, A equal to 0. Okay, when you put 0 here, you get U at this node, or U1 equal to A1, right? And you put X equal to L here. Okay, U at this node is U2 equal to A1 plus A2L. Okay, so from this two equation, you would have A2 would be equal to U2 minus U1 over L. Okay, after so this two equation, and you put this into here, and since A1 is U1, okay, so you would have Ux in terms of nodal degree freedom U1 and U2. Okay, like this. Okay, so basically you can have this one, and you will see that this one is N1 and this one would be N2. So this is like a linear approximation for this task element. So basically, so if you ask me, Ajahn, so what is this? It means that of course your displacement approximation for this task element is linear because it's involved linear function, you see, in the equation. And then, as you know, U1 and U2 are nodal degree freedom, and you would get their values after you solve your equation. Okay, so U1 and U2 basically would be your basic unknown. So once you know U1 and U2 here, and you want to know displacement within this element at any point, what you have to do is just put the value of x here, okay, in this equation, and you would get the solution of displacement at that point. Okay, so this is something about the thrust element. Okay, the first element that we saw. Okay, so for when you have a thrust problem or axially loaded member problems, okay, you can use this thrust element to solve, but you have to remember that it's assumed E and A are constant within that element. Okay, that you have to know. And those is anybody to know that one already. Okay. Next, we move to the beam element. So beam element would look like this because we assume that element is length L. Okay, and E and I are constant. Okay, E and I are constant, and within at each node, it involves through degree of freedom, that is theta or rotation, and W, which is vertical displacement or deflection at each node. Of course, at this node, nodal degree of freedom for beam element, of course, they have to be different from thrust element because for thrust problem, what we interested are the axial displacement, right, or elongation. But for the beam, what you need to know is rotation and deflection. So the nodal degree of freedom would be represented by this, and nodal force vector would be moment M and shear V. So this is basically represent a beam element with nodal variables. Now, what you need to do is similar to when we derive the thrust element. That is, we try to relate moment and shear with rotation and deflection. Okay, moment and shear. So basically, what we need is a equation like this, but for beam element. Okay, this equation for beam. We like to have equation like this for beam element. So basically, what we need to derive is element stiffness matrix for beam element that relate here, which not going to be U1, U2. Now it must be theta 1, W1 and theta 2, W2. And here it's not going to be axial force. It has to be moment and shear. Okay. And basically, I would say that all of you must have seen that equation before when you study, structural analysis at undergrad level. You would have that one. But anyway, we will repeat this again because also for within the context of finite element approximation here. Okay, so we start with approximation of deflection W here. Okay, for deflection, it represented by cubic approximation, okay, or cubic equation like this. Okay, you cannot use linear approximation for the deflection. Okay, now you have this. Of course, similar to what we do with the thrust element, we don't want this A. We try to eliminate A. What we need is, of course, relate W here with theta 1 W1 and theta 2 W2. So let's do that. Okay, we apply boundary conditions or end conditions here. Okay, like this deflection at 0, of course, would be equal to W1 and equal to A1, and then we apply slope, which is theta 1 at equal to 0, and then apply at the other end deflection and slope. You have this equation, and you're solving. You have 4 equations, right? These 4 equations. You have 4 unknown: A1, A2, A3, A4. You can solve it, and you can have A1, A2, A3, A4 in terms of all these variables, and you put the solution for A1, A2, A3, A4 back to the original equation, the cubic equation. You would have relationship between the deflection and other variables. So that's what I have done here. Okay, that's what I have done here. Okay, solving this equation for A1, A2, A3, A4, and once you have that one, you put it back into here, A1, A2, A3, A4, form that equation. You would get the solution here. Okay, and from this you can define shape function. Shape function similar to what we define shape function for thrust element like this. Okay, this is N1, this is N2. You can define the shape function for beam element similarly. Okay, and then what is you got is this. Okay, you have relationship between diffraction and nodal variability because they involve nodal variable diffraction at left node and theta at left node, diffraction at the right node and theta at the right node. Okay, and the relationship between this and this are obtained via this shape function. And so from this, after you rewrite this equation again, you would have shape function matrix in like this. Okay, n1, okay, n2, n3, and n4. All of these shape function are, I would say, a cubic function defined by polynomial of order 3. Polynomial of order 3. Okay, it has to be like that because your displacement approximation or diffraction approximation W are cubic approximation. So it's going to be a cubic function like this. Okay, and if you look at all of this, so what is N1? Okay, N1 is something like a diffraction at node 1, right? When rotation at node 1 and rotation and diffraction at the other node are all 0, right? Because you may be able to see this. Actually, I can write it. W1, right? Plus N2 theta 1, right? Plus N3 W2, right? Plus N4 theta 2, right? So N1 would be diffraction. Okay, when theta 1 W1, sorry, when theta 1 W1, also sorry, theta 1 W2 and theta 2 are all 0. So shape function would be equal to displacement here. And of course, when W1 is equal to 1. Same thing can be said for N2, N3, and N4. Okay, so this is the shape of the displacement within the element or beam element here. Like this, when you constrain other nodal variables. I think you may see this one, okay, especially if you study matrix structural analysis before, or okay, you will see this one before, this matrix. Now, so this is what we have here is a shape function for the beam element here. But what we need is actually the equation like this, right? What we want is K D equal to F, right? K D is of course nodal variable. F is nodal force vector. Okay, we want this matrix that relate nodal variables and nodal force vector. We don't have that at this time, so we need to derive this one. To do that, okay, okay, we start with apply the beam equation that we know, right? Moment equal to EI times second order derivative of diffraction, and shear is of course equal to a derivative of moment, okay, which is of course EI times third order derivative of diffraction. Okay, so you put this W, okay, as N D, right? So this is what you have, and then you want to relate, of course, KD equal to F, right? You want to relate F, which is moment and shear at the other node. So you have to apply the condition of moment and shear at node 1 and moment and shear at node 2. Okay, node 1 and node 2 here. This V1, M1 and V2, M2. Okay. So after you apply this equation for moment and this equation for shear, you put x equal to 0 and x equal to L to define moment and shear at both nodes. You would have this equation. Okay, and if you look at this equation, this is F, right? And inside all this equation, you have nodal variable, slope, and diffraction at both nodes. So after you set up the equation, you would have element stiffness matrix or element stiffness equation for so we can express the element equation for beam element like this. KD equal to F, because K would be the element stiffness matrix. Okay, relate the nodal force here, which involve shear and moment at both nodes. And the nodal displacement here would be theta on rotation and deflection W at both nodes. Okay, so this is the element equation for what is known as Euler-Bernoulli beam element, or sometimes people also know that as a thin beam. So it's the beam that we learn in mechanical materials at undergraduate level. Okay, that involves certain approximations. Okay, within its deformations. Okay, like that. And also for this element, and if you use this beam element in solving your certain problems, okay, it's implied that you ignore the axial deformations. You ignore the axial deformations. Okay, so if you want to improve the axial deformations, so that could be done really easily. Okay, your elements will look like this one. For each node, you would have 3 degree of freedoms. 3 degree of freedom. For each node, it involves 3 nodal variables. So in addition to theta and W, you would have to add the axial displacement at that node also. Okay, so basically it's like you incorporate touch element in here. And when you do that, your symptomatic K will look like this. Okay, so so this one is a element for fractional member. So basically like a problem like a truss, frames. You should use the element like this. Okay, to handle those problems. Okay, and this is element stiffness matrix. This is nodal displacement vectors, and this is nodal force vector. Okay. Okay. So right now you have 2 types of element that I show you, and of course it's not going to be I think it's not new to you, but anyway, just for completeness for the course, I just start with this one in our course and show you what are the elements equations for truss and beam problems. Okay, what the equation look like and how to derive it. Because this kind of element you can derive by using the basic equilibrium or all those things. Okay, so what you need to know now is you have equation that relate nodal displacement and nodal force like this. Okay, for truss element, this represent axial displacement. Nodal variable would be axial displacement, and for beam element, this one it would be rotation and direction. Okay, unless you want to add the axial displacement also, it's gonna be like this. Okay, for in our discussion, I don't think we're gonna consider this one. I can consider only the case with no axial deformation. So this would involve only rotation and deflection. And for force, for truss problem, it would be axial force, right? For beam, it will be moment and shear force at the node. Okay, and all this you see this equation for beam and truss. And one more thing that important is the shear function. Okay, the shear function for for truss element. Okay, should erase all this. Okay, for truss element, the shear function is like this. Okay, n1 and n2. Okay. Shear function is the function that approximate the field variables, or in this case, is axial displacement. Okay, form the nodal solution. Okay, for truss problem, the shear function is linear. Okay, it means that for this element you have a linear approximation. Okay, like this. And so this is the shear function for truss n1, and this is n2. You're gonna see this a lot. Okay, later. Okay, and for beam element, the shear function is like this. I think you may have seen this before. Anyway, okay, just now once we have this one, just look at the example. Okay, suppose we have just this simple problem. You have axially loaded member. You have the this a bar, say a bar, subject the axial force P. Okay, the bar is length M. Yeah, and this is not uniform cross-section bar, because the cross-section is varying according to this equation. I can say that it's linearly varying. Cross-section is linearly varying, okay, according to this equation. So it has larger cross-section here, and then it's become, reduced to this section. Okay, of course you can solve this problem using just simple mechanics. Okay, if you study, I think, second year or first year mechanics in your undergrad study, okay, you may be able to solve this one. Just integrate some equations, certain equation, and you would get what we call analytical solution. And this is what you're gonna get when you do it. Okay. This is solution for displacement, and this is solution for stress. Okay, you will see that it's going to be involve certain parameter in the solution, because I want it to be this solution is I would say dimensionless. Okay, a solution like this is a good way to solve when you solve for analytical solution. Okay. But anyway, so this is what we have, but we're not going to talk about that here, because this is finite element. But anyway, so if you ask me, John, if we don't want to talk about it, why? You show me. This is important, because if the problem involves analytical solution, okay, you should use it as a benchmark to check your FEM solution. Of course, our plan is not to use FEM solution for problems that have analytical solution, but at least when you develop your algorithm or your program, you should have something to check. And we usually, or I should say, we always start with the problem that we have analytical solution, so we can be sure that our program works, accurately. Anyway, so this is the solution that you're gonna get when you solve this problem using the basic mechanics, and you will get an analytical solution, and we will use this to compare our FEM solution. Okay. Now, let's solve it with FEM. We start with the modeling. Okay. So we start with two elements, because your actual problem is look like this, right? It's too much here. Okay. You discretize into two elements. Okay. This is element one and this is element two. But when you use a test element like this, you already assume that the cross section for each element must be uniform. Okay. So it's going to be this A1, A2. A1 to represent this element 1, and A2 is represent this element 2. So what you need is approximate A1, A2 for this non-uniformity here. Okay, so this is what we have. A1 would be like this: 0.875 A0. This is 0.625 A0. So now we start FEM modeling. We have this is what you should do. Okay, define element number. This is element number. Sorry, this is not. This is element number. You have two elements, so you have element 1, element 2, and you have node number here, node 1, node 2, node 3, like this. For each node, you have nodal variables defined for each node. So this is your FEM modeling. The simple one. We start with two elements using task elements. Okay, like this. So for each element, we use the matrix element simply matrix for task element. So you have like this. Okay, and the length L is of course LO2, because for each element you have, right, LO2 length. And then you assemble. Okay, remember that after you have the equation for each element, to solve for the nodal variables, you have to assemble all element equations. Okay, now you assemble. So this is come from element 1, of course, and this is come from element 2. So element 1 and element 2 have common nodal variable U2 here. Okay. From this is a global equation. Okay, to solve for this solution, what you need is apply boundary condition. And in this equation, at node 1, so you may ask, what is this? It's unknown reaction. Actually, you don't know. Actually, you know, but let's say for the time being, you don't know. Okay, and then this is another force vector at node 2 here, because it's 0. You don't have the force here, and you have force P here, right? So this is what we have, the global equation, and then you apply boundary condition. You want equal to 0, right? So you cross this out, first row and first column out, get the final global equation, and then you solve for this one. Okay, you get U1, U2. Oh, sorry, U2 and U3. Okay. Okay. If you want, let's say, look at this first. You have a solution for 2 elements first. Okay, this and this are the solution at the this is U2, right? This is U3, right? It means that after you solving this one, okay, it means this is U2, this is U3, and this is only thing that you have from FEM. Okay, so if you want to plot the graph, what you have is would be this. Okay, you have this displacement, right? This is X, right? And this is LO2, right? You have U, right? Displacement. You have only U2, something like this, and U3 is maybe something like this. You have only these two value from the FEM, and then you plot. You have this U2 and U3. Okay, but we know that if you use class elements, you assume linear approximation. It means that the element, the solution within each element are linear. So what you can do is, so this is U1 is 0 from the boundary condition. So what you can do is you just draw a straight line. You just draw a straight line. So this is U1, U2, and U3. Okay, this is we obtain from these two we obtain from FEM, and this one from boundary condition. And then the displacement within the element you draw straight line, which is the green line here. Okay, within element 1. And you have another green line here for element 2. Okay, it's a straight line. And now we want to compare for analytical solution. We already have that one, right? Analytical solution, and you plot the solution in this graph. You have a blue line here. Okay, and you will see that, oh, it's look very close. Okay, very close. Of course, it's not perfectly matched because we give some approximation, right? But at least, okay, it's so close for displacement. Now compare stress with analytical solution. The analytical solution is blue line here. What is the stress? We know from the derivation of, the class element, right? We have stress equal to E times strain, right? And equal to E times U2 minus U1 over L, right? Something like this, right? So for each element, you have displacement at the right node and so basically, it's the stress is the Young modulus times the difference between the displacement between the right node and left node divided by L. So from this, the whole thing, whatever they are, it is a constant. So it means that for each element, strain are constant. Stress are also constant for a class element. This happens when you use linear approximation for displacement here. You know that the displacement is basically strain is the derivative of the displacement, right? So if displacement is linear, then strain is of course a constant. So for each element, the stress would be constant. So for this problem, if you look at the element 1, stress would be like this, constant, something like 1.1 something. Okay. For element 2, the stress would be equal to this, 1.6 something. Okay, you can compute that by yourself. Okay, we have a solution. So this is remember that this is normalized. So you have to normalize the same as we normalize the solution for analytical solution. Okay, so if you look at this, you may say, Ajahn, it's look, it's not quite accurate like the test. It's look, it's okay around here, the test, but somewhere around here is quite off. Okay, the approximation somewhere around here. So if you want more accurate solution, especially in terms of stress, you can do that by using more elements. Instead of 2 elements, you can increase to 4 elements. Okay, so this is what we have, right? And also 8 elements. Okay, and also 8 elements. So this is the solution when you increase the number of elements. And if you look at the graph here, for 4 elements, okay, you have U1 from boundary condition, and the solution gives you U2, U3, U4, U5. Course is look closer to analytical solution, of course, because you use more elements, and space is also, at least it's closer, even though it still look, quite off, because it gives you like a step function here. This the space. Okay, if you want more accurate space, of course, you have to, use more element. Eventually, you may have something like this if you use more element. So possible that you may have something like this. Okay? Use more element. But of course, in that case, you have to decide what you like to do. If you want just displacement, maybe it's okay to use, lower number of elements. But if you want accurate stress, then you may have to, in this case, use more element. But of course, increasing number of element, okay, is not the only way to get more accurate solution. Okay, I just mentioned this. This, and we will see it later. Okay. Now, if you plot the tip displacement, you want to see convergence, right? You have this, right? And you want to find this is a tip displacement. Okay. Analytical solution would be like this. And if you use 2 elements, so this is a solution for U3. Okay. It's look far. It's not that far actually, but when you put all these value in this scale, it look quite far. Anyway, if you use 4 elements, so this is 5. It's getting closer. And when you use 8 elements, this is U9. It's getting closer and closer once you use more elements. So in this case, you can say that it's like a solution. Your solution is a converge to the analytical one. Okay, analytical one normally. But if you look at this, you may notice that, okay, if you ask yourself, it look like the FEM solution always less than the exact one. In this case, okay, at least in this case, it look like it's less than the exact one. It's like it's one sometimes, okay. When you look at this, okay, if you increase to maybe 20 element, it may go to here, but it's still maybe less than the exact one, which is possible because it looks like your FEM is more stiff or stiffer, okay, stiffer than the actual model. It's stiffer, okay, stiffer. So this is sometimes you may see it in this like a simulate method, okay, it gives you the stiffer model. Now, okay, let's move to the other example, involve beam. Okay, this is like a very simple beam problem. You can solve this, of course, using whatever knowledge you have. Even though I'm not sure whether you still have that right now, like a method of consistent deformation, consistent deformation, or maybe slope deflection, or moment distribution, or whatever you can use that one to solve, of course, and you will get solution. Of course, you can do that. But right now we will focus on FEM solution. Of course, we ignore the axial deformation, okay, and then here is constant. Okay? You have the applied nodal force here. Okay, now we start with 2 elements first. Okay, 2 elements here. We have element number, F node number like this, and then for each element you have this nodal variable and force, nodal force vector defined like this for each element. And your simple matrix K for each element is defined like this. Of course, you can take that from what we have before. And for this problem, LE is what? 3 meters. Okay, 3 meters. Now you apply assemble, I would say you assemble this element equation for each element. You have this global equation. Okay, and then you apply boundary conditions. So from this, okay, from this problems here, diffraction and rotation or slope are 0. So you cross this out. This is cross reaction here, which for the time being, okay, just eliminate it. And the other one is of course here. Diffraction is 0 here. Okay, this and this are 0. And V3 become reaction at this point. So you did not add 3 by 3 matrix to be solved. And of course, you have applied nodal force. Okay, V2 here is minus 100 because it has to be, I think, upward to be positive, right? And M2 would be 100 because it's counterclockwise. M3 is equal to 0, no force, no moment applied at the right support here. Okay, and from this, I think eventually you have this final global equation to be solved. And after you solve, okay, I think this is a solution that I have. Okay, try and solve by yourself. I have a question. So this is for 2 elements. Okay. You have nodal variables here. First, whether this is exact or not. Okay, so that is okay. If you solve it by using maybe slope diffraction, will you get diffraction and slope here and also slope here the same as here? That's the question. Okay, whether you get the same if you use your method that you study from structural analysis at undergrad level. Okay, whether it's the same. If they are the same, why? Of course, if they're not the same, you may say, Ajahn, I can improve the solution by using more elements. But I can tell you right now that they are the same. Whether you're using this FEM or just using slope diffraction or the consistent deformations or whatever method that you saw analytically from the beam equation to get the solution here, you get the same. Okay, you get the same. So the answer to this question is no. Okay, but the reason why, okay, I give you time to think about it, and maybe next week, okay, if you raise this question, we can discuss in the class next week. Okay, and maybe you will see maybe the answer to this question maybe okay can be answered later, in this slide also. Now, what you see here is the case, the 2 example that for beams and truss, but you have the applied load applied at the node. Now, if you have a load that applies within the element length, how could we handle it? Because the equation that we have is something like this, right? Ku or Kd equal to F, right? So if you have the F as nodal force, at only the load that apply at the node, so it's okay. But if you have the load that apply within the element, how could we transform that load into the node? Actually, you can do it by applying this equation. So basically, you have to integrate the product between the load and the shape function matrix, and from that, you can obtain the nodal force for the problem. Okay, for the problem. So this is sometime in some books they said it's called the consistent loading. Okay, for example, if you have a truss element and you have the applied force, this Qx distributed along the element length, and you want to solve it using the FEM. Basically, you want to transform it into the nodal force. Okay, F1 and F2, because you want to adopt this equation, right? So you want F1 and F2. F1 and F2 can be obtained from the integration between the loading and the shape function like this. From the loading and shape function like this. So basically, when you apply this equation, you can obtain the nodal force. Okay, so this is a sample for our element. Okay, for beam element, the same thing. So for beam element, let's say you have a distributed load W. Okay, it doesn't have to be uniform. Or it could be uniform, of course, but it doesn't have to be any function W. Okay, and you want to transform this loading into the nodal force, moment, and shear. Okay, you can also do it by this integration. Okay, and let's look at the example of uniform load, because this is basically easy to do. Okay, so from this, if you have a uniform load applied over the beam element of length L, the nodal force V1 and M1 can obtain like this. And V2, M2 also. Okay, and we obtain like this. So you see that this is like a fixed in moment, right? In slope deflection and moment distribution method, right? So this is how you obtain a nodal force from the distributed load. Of course, if this W is not uniform, okay, you just perform integration and you can obtain all those, nodal force vectors. Okay. So let's look at, suppose you have uniform load here like this. Okay. Let's try one element. Okay, uniform load one element. So the nodal force vector for this, okay, we have this because we got this from the previous page. Okay, and this is the equation, the global equation, because we have only one element. We don't have to assemble. We have one element. Just adopt the element equation like this, and then apply boundary conditions. So the final equation would be like this, because the W1 and theta1 out put it equal to 0, you get this, and you have the solution. So this is exact solution. Exact solution, I mean, if you solve uniform load W of length L, deflection would be WL, right? 24, oh, so sorry, 8 EI, right? Okay, which is this one. And rotation at this node would be WL cube over, of course, 6 EI. Okay, also exact one, the same that what we obtained FEM, the same for nodal solution. Now let me ask you this. Deflected shape, whether it's exact. Of course, you can obtain object Ux would be what? N1 W1, right? Plus N2 W2, right? Plus N3 W3, right? Plus N4, sorry, theta 1, right? So N2 theta 1, right? N3 W2, right? N4 theta 2, right? Okay. Right. Let me see what's okay. Just want to show you here. So you okay. So you have this, right? W here, right? N1 W equal to N1 W1 plus N2 theta 1, right? Plus N3 W2 plus N4 theta 2, right? So now in our case, W1 and theta 1 is 0, right? You have for this problem. Go back. So you would have Wx, which is the deflected shape, would be equal to N3 W2 plus N4 theta 2, right? So this is the shape that we obtain from FEM. The question is it exact? Exact mean whether you're going to get this from analytical solution by solving the beam problem, by solving the beam equation. The answer is, I can tell you there is no. Because the exact shape, because the shape from FEM here, you approximate by cubic equation. So basically Wx here is a function of order 3, polynomial of order 3, right? But for this problem, the deflected shape would be order 4. Our polynomial of order 4. So it's different order. So that's why FEM solution here, the deflected shape is not exact. So why is that? Why is order 4? Okay, you have to go back to the beam equation. Okay, something like this, right? The equation is something like this, right? 4, right? Go to, let's say, Qx, right? Okay, something like this. So if you have the loading here, like a given constant, so it means that W must be order 4. So basically, if you have the loading applied, distribute load applied over the element, the deflected shape would have the higher order than the shape from FEM. Okay. So in that case, it's not exact. Okay, it's not exact. So you can get close to the exact one by maybe just using more element. So I leave you the question here about bending moment, whether it's exact. Okay, and what about if EI is not constant? So this one maybe you can just answer to me now that okay, use more element. Okay, because it can handle only the element as assumption is constant cross section or constant EI. So if EI is not constant, you use more. Okay, like previous example. Okay, with this, you can answer me now that. Okay, yeah. Can we improve the accuracy by using more element? In this case, I already said to you no, because this one already exact, right? The deflected shape is also exact actually, because for this problem, this particular problem, the shape is cubic. It's exactly the same as the FEM approximation. Okay. I think after this, I have something about something like this, which I'm not gonna put into detail. Just put it here for completeness. Okay, just put it here for completeness because normally the truss and frame structures are found in different orientation. So the element that we see before is just use only the same orientation, so it's easy to apply. But if you have the beam and frame that have element with various orientation, so in that case, we need a coordinate transformation. Basically, you transform all matrices into global and then apply. Okay, I just put here some basically that you need to know at least for trust problem. Okay, so for this one, I stop here right now, and maybe next, if you have questions about this, maybe we can discuss in the class and move to the next. Okay, bye for now. Yeah.